Oh my God, guys, I'm so excited because this week we get to learn conservation of energy. And as I've been saying, this is my favorite thing to teach in all of physics because it is another one of those things in physics that is so simple and yet so powerful at the same time. It is something where you can know very little about a certain situation and being able to make kind of wild predictions about the future. Okay? And I'm excited to share that with you and get there with you, but before we get there, we need to first talk about potential energy, okay? Which is the second major class of energy that we talk about in this class. Now, to keep the money analogy going, we could think of potential energy as kind of like the bank accounts, right? So if we think of energy as like the currency of the universe, right? The money that the universe uses to make transactions and make things happen, right? Potential energy are like the banks. And they store energy, and you can pull that energy out to use it to make cool things happen in the real world, right? Now, potential energy often is confused in the sense that people think that it's only gravitational potential energy, that you only have potential energy if you're like high at some level, right? But that's not the case. There are several different types of potential energy, and I am going to share them with you here. So if you guys can go to the slide that says, what is potential energy? So in the top left-hand corner, there's the ball of rubber bands. That would be elastic potential energy, right? Anytime that you have some kind of elastic that you can stretch, you're storing energy because when you let go, it can do work and add kinetic energy to something. Classic example is a slingshot, okay? If you go one to the right over from that, you see a battery. Any guesses? Yes, that would be chemical potential energy. That is the energy that's stored inside of the bonds of different molecules, and that energy can be harnessed to do work in the real world. You have this picture on the lower left-hand corner of a mountain. That's no big surprise. Gravitational potential energy. That is the energy that you have simply by being at an elevated height in some kind of a gravitational field, because that elevated height can then be converted into kinetic energy if you were to drop something or jump or fall, right? And then, of course, the most powerful and devastating of the potential energies is nuclear potential energy. And that is the energy that's stored inside the nucleus, inside the strong nuclear force that's binding all those protons and neutrons together inside the nucleus. This is the kind of energy where just a few grams of nuclei can actually result in a massive atomic explosion that can level a city. It's kind of wild to even think about. So if you guys can go to the next slide, this is build your own equation. We're going to start with gravitational potential energy, and I'm going to ask the question, what should gravitational potential energy depend on? Okay? Just like we did with kinetic energy, right? With kinetic energy, we said, well, it must depend on velocity because it's the energy of motion, right? What must gravitational potential energy depend on? Okay? And so I'll give you guys a second to think about it. I'm going to write a PE on here. That's for potential energy. Usually, I will use potential energy as PE. Sometimes some textbooks and online use it as a U for potential energy, but we're going to focus on PE, okay? It's hard to forget. So think about it. Maybe make a list. Pause the video if you need to. What should potential energy depend on? Well, you might think, well, the higher I am, the more potential energy I'm going to have. And you would be correct. So the height of an object, h, is something that potential energy depends on. So, okay. What else does potential energy depend on? Well, I would have to say that if I were on Mount Everest on Earth compared to something like Mount Everest on the moon, I'd have more potential energy on the Earth, because on the moon, I would just like lollygag down to the ground, right? I mean, eventually you'd gain enough velocity where it would be a pretty painful impact with the ground. But it does imply that gravity must have something to do with how much potential energy you have, and that is true. So the acceleration due to gravity is a determining factor of potential energy, okay? And lastly, you would imagine that a little, maybe marble versus a bowling ball at the top of Mount Everest would have different potential energies, right? So it must mean that mass somehow determines how big the potential energy of an object would be. So I'm going to put mass there as well. Okay? So I am positing to you that potential energy is due to mass of an object, how many kilograms it has, how much material it's made out of. G, what is the gravitational acceleration of the planet that we're dealing with, right? And H, how high above some relative position are you, okay? And that'll be our potential energy. So this is gravity, and this is mass. And so I'm going to ask the question, how did we do? If you guys could go to the next slide, and you see, heck yeah, that is exactly the equation that we were supposed to get. Yeah, it's almost like I knew or something. Crazy. So let's do a little problem. Let's see how this works, okay? So we have this problem with the cricket that I write down here. So imagine a friendly cricket has a mass of 2 grams, right? So we can already start writing that down. I'll start writing some stuff down. We have mass equals 2 grams is going to be 0.002 kilograms, right? Okay. Imagine the same cricket now jumps straight up with no angle at a speed of v equals 1.73. So my little cricket guy is jumping up with a speed of 1.73 meters per second. Okay, and the question is, what is our cricket's maximum height? And hint, hint, the reason why I'm asking you to find the cricket's maximum height is because we're going to need it to get his potential energy. Okay, so hopefully you guys realize that physics is something that builds on itself, and that you know how to do this from a previous chapter, and that chapter would be kinematics, right? So I simply need to write V1, V2, A, D, and T. I got all these guys. My cricket starts out with a velocity of 1.73. Maybe if you remember, if you dust the cobwebs off your brain from a few chapters ago, at the maximum height, V2 equals 0, right? And you probably know that gravity is negative 9.8 meters per second squared, right? And you also probably know that this, D, is what we're looking for, okay? So what equation would we use if we want to find D and we have V1, V2, and A? No big surprise here. We simply use V2 squared equals V1 squared plus 2AD. V2 is 0. This is 0 squared. V1 is 1.73 squared plus 2 times negative 9.8 times D. Now, if I solve for D, this is going to get subtracted to the other side. Negative signs are going to cancel out, okay? And for my D, I get a value of about 15 centimeters, or 0.15 meters, right? So this guy, this little guy, is able to jump 0.15 meters up into the air, which makes sense. Little crickets. If you've ever seen them jump, that seems like a pretty reasonable jump. Now, the question is, what potential energy does he have at that height? Okay, and nothing too big of a surprise here. This is simply a plug and chug into our fabulous little potential energy equation here. We know that potential energy is mgh. Okay, we know that the mass of this guy is very small, 0.002 kilograms, right? Times gravity, 9.8 meters per second squared, times the height that we get to, which is 0.15 meters. Okay, and I multiply all those guys together. The potential energy that this little tiny, annoying, loud cricket, I'm just kidding, I love crickets, but they do get annoying if they get in your house. The potential energy this guy will have is a mere 0.003 joules, or 3 millijoules. Check me if I'm wrong. Okay. In the next video, we're going to begin exploring 2 different kinds of forces And these are extremely important to be able to tell the difference between in order to do conservation of energy problems. These are called conservative and non-conservative forces. I'll see you there.